recorder. Okay, everything ready. Okay, it is recording.
Check
Good.
the space.
Definitely. Let's do it. Oh. Mhm. Oh, no, DF. Yep, we've got enough space. Oh, that's from Sac City.
Thank you.
You're welcome. This thing is, once I close it, I can reattach it to my keychain. Yep.
Handy.
Very handy. It looks like a key too.
So nobody ever knows.
Especially the TSA.
Does it count as a hidden weapon?
It is a key. It is a key. Yep.
It is the key to my way out of here.
Well, because of my flight to Canada, at least with Delta, the pilot or the flight attendant would tell all the passengers, you cannot use a Samsung Galaxy S7 in flight. So if you do own one of those devices, you have to hand it to the flight attendant, and she would put it in a cabinet, I guess, fire and explosion proof during the flight. At the end of, huh?
They have such a cabinet?
I don't think it's actually explosion proof, but I think they would ask you to turn it off and then they'll put it in a place where it's safe. Yep. I'm pretty sure that's doing wonders to the reputation of Samsung.
You can still buy an S7
Huh?
at Best Buy.
I think it's the Note 7.
It's the Note.
It's the Note 7.
Maybe. All right. So let's go ahead and get started. And I'm expecting to have even fewer people next week because it's Thanksgiving week, right? Most people will be staying home and get their turkey ready.
Thursday's no class too.
There's no class on Thursday, but there is class on Tuesday.
There's an exam on Tuesday.
There's an exam on Tuesday, that's right. Okay. So, in order to prepare you guys for the exam, I have done some work, okay? And you can see that this file has been renamed from processor.txt to messy opcode description, which means, well, it's something that we start off with, but it's not necessarily the best thing that you can use in the exam. So the next one is new. Okay, you can see the timestamp. This one is the last modification time is 8:28 a.m. this morning, and then the other one is last modified at 8:30 a.m. this morning. So let me just open this up and show you what it has. So this one basically has exactly the same information, except it is formatted in a very clean way, and it is a spreadsheet. So it's a table. It's easy to print it out, and you can download it, modify any way you want. Add your own formatting, add your own annotation. If you want to put all the slices of the microcode, do it. Okay. So this document is just like any other document in that folder. You can read it. You can make a copy of it, and do whatever you think you need to do with it. Okay, but I'll just quickly explain what each line or each cell of this particular spreadsheet. The first two are fairly simple, and I think most people should know by now. XX specifies one of the four registers. A is 0, 0, B is 0, 1, C is 1, 0, and D is 1, 1. Same thing with YY. Okay, so XX and YY are placeholders for the bits to specify a register out of 4. I, lowercase I, is basically a constant value that has to be determined at assemble time, which means it cannot change at runtime. Once you fix it, it cannot change over time. Then we have the flags. Okay, C is carry, Z is 0, S is sign, O is overflow. The L flag is really the exclusive OR between the sign and the overflow flag. So we talked about that as well in this class. And then all registers and memory locations are 8-bit wide. Okay, so this way there's no confusion of, okay, how many bits are we talking about? They're all 8-bit wide. So the rest of the table is really just an opcode table. Okay, this column is representing all the opcodes in bits. Okay, that's not what I want. Change the width a little bit too much. There we go. So these are all opcodes in binary. You can see some of these have just zeros and ones, and others have XX and XXYY. So it depends on what kind of instruction we are talking about. This column talks about the mnemonic, which are basically the kind of slightly easier to remember name of these particular opcodes. So we have no op, halt, CPR stands for copy register, and so on. And you can read the description to find out how the mnemonic becomes the mnemonic. It's not that important that you have to memorize or have to use the exact mnemonic, because as long as I understand what you are trying to say, that's fine. Okay, because I am not like the actual assembler, picking all the spellings, uppercase, lowercase, and stuff like that. Okay. The only time that you really have to be very, very careful is when you're dealing with something like this. Between the LDI and the Ldi instruction, it is very specific. Okay, LDI is completely different from LD. Okay, so you have to make sure that you do not have an extra I, when you actually mean LD, or vice versa. The conditional branch instructions are also very specific. In other words, you do have to indicate exactly which flag is used for the conditional branch. Okay, you cannot, you have to make that very clear. Let's see, what else do I have here? We have the C notation column. Okay, so the C notation column is exactly what the name implies. It is using the C notation to indicate what a particular opcode is going to do. So hopefully you still remember stuff from your cisp310. Okay, and we have been using this notation quite a bit in this class. Some are sort of new, and most are not really new. So I will start with the first one. No op, I use open and close brace to indicate no op, because in C and C++, that's an empty block. It doesn't do a single thing. Okay, it doesn't branch, it doesn't do any calculations, it simply does not do a single thing. But after the comment, the // I say it is decoding whatever is the piece the program counter is pointing at, and it will also post-increment the program counter. So those are the side effects of the no-op instruction, which is kind of important. The next one is the exit 1. Okay, halt is equivalent to exit 1, which basically means I'm done with this program. Get me out of here. Except you cannot get the program, you cannot get the processor out of there when it's done. So it's basically stuck forever with the halt instruction. Once you execute the halt instruction, there's no way to get out of the halt instruction. Is that okay? But in terms of concept, it is the same as exit 1 in a C program, which means I'm done. Okay, get me out of here. CPR is just copying the content of one register to the other one. So in this case, Y is copied to X. Okay, it's cloning or just copying the bit pattern. The way I express conditional branch is a little bit different from the other one. In here, I'm using the ternary operator, which consists of the question mark separating the condition and the true value, and in the colon, which separates the true value from the false value. How many people still remember the ternary operator? Okay, if you do not remember, look it up. Okay, this is actually a really useful operator in C and C++. It's basic, it's really fundamental to C and C++. It's a quick way to perform conditional stuff in an expression without an actual conditional statement. So just to give you a very quick explanation, when you have a ternary operator, the L in this case is the condition. If the condition is true, this is the value of the ternary operator. If the condition is false, then PC is the value of the ternary operator. So that's the actual meaning of a ternary operator. Okay. Let's see. We have the LDI instruction, and in here I made it a little bit more specific than in the other stuff. Okay. I'm basically saying the operation is really just copying whatever is at the program counter at that point of time to register X. But because the program counter is also incremented after the decode, so this means we are the program counter is already pointing to the byte right after the opcode when you execute the Ldi instruction. So, and that particular piece of memory is going to have a particular value. So star PC equals equal I is basically just indicating that the location right after the opcode has a value of I, which is a constant. And we are putting that constant into register X. In other words, it's just another way to spell out what Ldi does. Okay? And then we have the the actual instructions that access memory. One is LD and the other one is ST. LD is loading the content of a memory location into a register. So the direction is from memory into a register. ST, on the other hand, goes the opposite direction. We are storing the value of a register into a memory, the content of a memory location. But in both cases, the location in memory is dictated by register Y, okay, which is YY, which can be one of the 4 registers. So are we doing okay so far with all of these explanations? Okay, just let me know if you have any questions. Okay, we have conditional branches and unconditional, a single unconditional branch, which is just jump X, and that one is just changing the program counter to whatever register X has. Okay, once again, X is either A, B, C, or D. And then we have a whole bunch of calculation opcodes. Okay, so those calculation opcodes, they all go through the ALU. So not, and then we have the AND, OR, and compare. So all of these instructions will go through the ALU, and as a result, the flags will be affected by these instructions. Okay, not all flags are affected by all instructions. For instance, the right shift operation does not change the L flag. It does not change the overflow flag, because it doesn't make any sense. Okay, when you're right shifting, what does it mean when the sign does not make sense as the result? Doesn't make sense. Okay, so the right shift operator does not change the O flag, and as a result, it does not change the L flag either. But it does change the other 3 flags potentially. It will affect the carry flag. Well, no, it doesn't change the carry flag either. It will only change the 0 flag if the end result is 0, and it will also change the sign flag. Okay, because the sign flag is really just the most significant bit. So whatever the result is, the most significant bit is the sign flag. So it will change those 2 flags, but not the other 2. I think we just went through all the instructions. Are there any questions about this table? Is it better? I mean, it does look cleaner. Yep, cool. And I found, well, I was in the process of finding a way to generate all the opcodes, like using a single, nifty command to go through all the executable and generate something, but I couldn't get it done. But I can show you what I have found so far. So maybe some of you, or maybe myself, during the lab time, can finish this up and actually figure out the whole thing. But I'll show you what I have found so far. Okay. And we go to opcodes like that. Okay, so here's the thing. Okay, the find command is actually quite useful. So I can use a find dot dash regex, which it stands for regular expression. If you do not know what is regular expression, in your spare time, okay, don't do it right before the exam, okay. But in your spare time, you might want to make it a point to kind of check out what is regular expression, because it allows you to specify a pattern to match a string. We are not talking about just matching directly a string. You can use wildcards, you can use any number of blah, 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 and so on. So I'm going to use this command here. You have to specify what kind of regular expression, because there are different dialects of regular expression. So the one that we are using here is called grep, okay, which is a command in most Linux implementation. So it's really used a lot. So the regular expression allows you to specify, backslash dot is basically just escaping a dot, because a single dot or the period has a special meaning. So if you don't put a backslash in front of it, it's going to have that special meaning. But in this case, I don't want to have that special meaning. I really literally want a single period. And then the slash has no particular special meaning, so a slash does not need to be escaped. And then here is the fun part. I can specify a-z to mean a single character from A to Z, lowercase a to Z. Is that okay? Yep, go ahead.
I was just gonna say, I don't remember the exact website, but I know there's a website that has all the regular expressions in there, so that if you wanted to find out what a particular expression is, to find, whatever it is you're looking for.
Well, you kind of have to be able to express what you're looking for, and in the process of specifying what you're looking for, you probably can generate your own regular expression. You're talking about the syntax part being a little bit difficult to specify, right?
I don't know if the syntax, well, you can actually test it though.
Okay.
Like you can go in there, you can type something, and it'll show you what it's grabbing.
Okay. Well, I'm doing the same thing here. I'm testing it. The find command does not do anything harmful to the files. So it's basically just listing the files that fit a particular description or criteria, set of criteria. So in this case, I'm just using the file name as a criteria that has to fit a particular regular expression. So it's not going to do anything bad. You can experiment without actually worrying that it will do any harm to the files in this folder. So in this case, I also use backslash open brace and backslash close brace. Okay. Those two are particularly useful because inside you can specify the number of occurrences of what is right before that. So in this case, what is right before the braces is the specification of a character from A to Z. So what I'm specifying now is to say we can have 2 up to 3 of those things, but it cannot be 4, cannot be 1. It has to be 2 to 3 characters, and each one has to be a lowercase letter from A to Z. Is that okay? So let's see if I do this correctly. So now we can actually list every single thing that is a command in this particular file. Okay, they're all between 2 to 3 characters long. So the next question is, now that we have a list of all the executables that we find are useful, how do we combine these, right? How do we combine all of these into one single command with a pipe symbol? I was kind of stuck at that stage when it's time to come here, okay? So one thing you can do is you can pipe this to another command. Now there's a command called tr, which basically translates, okay? It translates, but the problem with tr is it can only translate one character to another character. So you can translate the \n, which is a line feed character, to a single bar, okay, like so. So that so it would turn the previous output, which are all the commands are separated by line feeds, into something that looks like this, which is close to what we want, okay, with a vertical bar between all the executables. Okay. Then the next question is, well, we don't want to look at this. It looks nice, but we want it to actually run as commands. Okay. So there's another way you can execute a command like this. Okay, so let's say we use a command echo ls. Okay, echo is basically quote unquote print. In the case of the shell. Okay, whatever you specify, it will just print it out to the standard output. So it's not really running or executing the command. All it does is to show the command it will send it to standard output file. That's all it does. But you can also put a backtick around something that will print something to standard output, and then it will just go ahead and execute that as if it is a command. Is that okay? All right. So the problem that I have is it does not recognize the pipe symbol when it is inside the backtick. So if I do something like this, ls-sort, okay, it doesn't know how to do it. Okay, it says cannot access bar because it doesn't understand the bar is actually a shell command. So I was actually stuck at this point. I was able to format everything. I just could not get the command that already has all the pipe symbols to execute. So that was kind of where I was stuck right before the class. Can probably figure it out, during the lab time. But that's kind of like just making things a little bit easier to deal with, because otherwise you guys would have to run that long command to get it all done.
Aren't you just going to dump all that into a script though?
Yes, but I want to be able to add new commands to the make file. and not having to do a lot of duplicate work to get it to work. So I want to be able to just add a new command, and the makefile can automatically, regenerate everything accordingly.
By doing the whole find thing.
Yep. Mm-hmm.
But this won't grab a alt or any other 4 or more character programs, right?
That is correct. It will only limit to 2 to 3 characters.
Couldn't you use something like a file and then grab the document and see if there's an elf in there, and if it is, it's an alpha executable, and then just create a big list of all those. That way you can be 20 characters and also grab it.
Yep.
Find dash executable. Why not?
I think I found a way to do it. Okay. Okay. In my office, I actually have this, modified a little bit. So let me turn off syntax highlighting first, because that's really making it harder for you guys to read. So in my office, I already have something that's more like this. Okay, so let me you want to do a paste here. There we go. So in my office, before I came to this class, I defined a new, opcodes. They call it a variable. Okay, so opcodes is a variable. So in the next line, what I did was to refer to just opcodes here, okay, which is a shorthand. Okay, so here I'm listing all the C source files, but the opcodes are also representing the actual opcodes that I want to implement. So using this, I no longer need to use list out all of these things. So instead of doing this, I was able to do this: opcodes : replace the extension .c. Okay, let me see, with nothing. So what this does is it is referring to the definition of opcodes, but we'll go through every single item in opcodes and replace the extension .c with nothing. So noop.c becomes just noop, cpr.c becomes cpr, and so on. Okay, so there's this internal ability inside the make utility program to do substitution based on extension. Okay. So something just occurred to me. It's like, can I abuse this command, this ability, to do something that it was never intended to do? So we'll give it a try and see if this works. Okay. So gen all is going to rely on opcodes, and we replace all the .c with nothing, because I need those commands in order to generate the actual slices of microcode. So here's the command, and let me see if I can do it. So empty.rom is the first one. Okay, so there's no way to avoid having to do the cat empty.rom. So I'm going to pipe it to the following. The following is opcodes. Okay, in parentheses, opcodes, and I'm replacing the extension .c with a vertical bar. Oh, but then it doesn't have the /. Darn it. Okay, that won't work. All right. Well, I'm gonna look into this and find out, how to get it to work. But at least with this, all thing, I can now, also make the clean a little bit cleaner. No pun intended.
Maybe if you put the / in the opcodes variable for every C file.
That will do it, but it's very cumbersome. Yep.
What if you just run a shell script that generates the output?
You could do that. I was trying to avoid, using a script that is outside of the makefile. I was trying to use just makefile and the existing commands to do it. But if you use a script, yeah, you can definitely do it that way. You can quite easily use a Perl script, for instance, to locate all those files and then make your own command, or do something similar to that. But I was trying to avoid having to do a full up Perl program to do it, or Python, or whatever scripting language. So anyway, just a little bit of extra work that I have done so far, with generating the code. But in the exam, what you really should be focusing on is really just what the instructions are doing, except for maybe 1 or 2 questions that will involve the use of microcodes. So in those cases, you will need to know the schematic of the processor for the most part, and then figure out what values you have to specify for each item in those 26 bits.
Exams on Monday, right?
The test is on Tuesday.
It's the same processor.
Same processor. Yep. I thought about having you guys to modify the processor and say, okay, what if I want to support this new command? What changes do you have to make to the processor? Then I thought about it. They're like, well, that is a little bit too involved, and on top of that, it's very hard for me to grade. So let's not do that. All right. So, do we have any questions regarding the toy processor? Which basically, I really think it does have all the instructions, to do any type of programming that we need to do. It's just very, very tedious. Okay. Is that okay? All right. So if this is okay, what we'll do next, okay, since I'm using this method, we might as well just put most of the notes in Google Documents so that you guys have access to it during class as well as after class. So even if the recorder is, for some reason, is not recording, you still have the actual document that we work on during class. So I'm gonna do another. I'm just trying to decide between Google Doc and Google Sheets. I'll do Google Sheets because it's a table. It is a little bit easier for me to arrange things, in this case. All right. So what we want to do now is to switch back to the i86 instruction set. So I'm going to rename this to i386 instructions. Okay. And we have already started to talk about this a little bit. Okay. We have different types of registers. We have 8-bit registers, we have 16-bit registers, and then we have 32-bit registers. But that's one big fat lie. Because what we really have are 32-bit registers. All of the other ones are basically smaller windows into the big 32-bit registers. Is that okay? So we don't really have independent and separate 8-bit or 16-bit registers. The so-called 8 or 16-bit registers are windows into the 32-bit registers. Is that okay? All right. So that's kind of important. But what I want to focus today is to talk about the addressing mode. This stuff is not going to be in the exam. So unless you guys have any additional questions regarding the exam, we are moving on to talk about stuff that we actually need to do by the end of the semester. So the move instruction is MOV, okay? And it has got, I'm using this as optional, okay? So the optional part can have a B for a byte, a W for a word, or L for a long, okay? B is a byte, which means it is how wide? How many bits?
4 bits.
A byte is 8 bits, okay? A byte is 8-bit wide, a word is 16-bit wide, and an L is a 32-bit wide, okay? So you can control the actual width of the move, or remember, move is a misnomer. You cannot actually move data. You can only copy. Okay, so move is really just copy. And then it takes 2 operands because you have to specify the source and the destination. Okay, so I'm going to use SRC to represent source and DEST to represent destination. And I'm going to use both, italic here. Okay, doesn't like that. How about here, italic? There we go. Okay, so now the question is, okay, this is the general format of a move instruction, which in a way is very confusing because the LD and the ST and the LDI command that we use in the toy processor has the destination as the first operand instead of the second operand. So you just have to kind of keep in mind that the AT&T notation, which is what we are using here, specifies the destination as the second operand and not the first operand. Okay? So essentially, what this is really doing is saying destination equals source. That's what it's doing. If you look at the C notation, this is what it's doing. The question is, what can be specified as a source? What can be specified as a destination? So in today's class, I'm going to introduce the addressing modes of the Intel i386 processor, which is not unsimilar to the one that we have dealt with, to the toy processor, except they have more options. Okay, but the basic concepts are still pretty much the same. Is that okay? All right. So we're now dealing with operands, okay? Different types of operands. operand addressing. Okay, it's called addressing mode, but it is really a misnomer because it is not really an addressing mode. It's just being able to specify different things. Okay, so different addressing modes, we can have a $ followed by some kind of expression. So I would use italic expr here to mean any type of expression. It can be as simple as 0, constant. It can be a label, okay, it can be L1, L2, where the label is defined somewhere else. It can be an expression like what is x times y plus z, okay? So it can be anything. The point is this expression has to be resolvable, or it has to be computable by the time we assemble the program. Is that okay? So I'll just explain here. EXPR has to be resolved at, well, I call it link time, okay? But basically to you, as far as what we have done so far is assemble time. So I will talk about the distinction a little bit later because at this point there's no need to differentiate between those two. And the name of this is called immediate. The addressing mode itself is called the immediate addressing mode. Don't ask me why they chose that name, but that's the name that Intel has chosen for specifying a constant. Okay, and here we'll talk about how does this relate to what we have done so far. Okay, this is actually the second operand of our LDI instruction. Remember, in the LDI instruction, there's an I here. This I over here, that is our immediate constant. It is the same concept. It is simply a bit pattern that is right after the opcode that you're going to copy to a register or some other destination. The Intel processor does allow you to specify, a lot of kind of more fancy instructions. Do we have any questions about role 4, okay, or the idea of an immediate operand?
So LDI X I is like
The I is in italic.
immediate from X to I.
No, it's the other way around. X equals I.
The destination source. Okay. So load immediately from I.
Because
to
in
X.
our toy processor mnemonic, the first operand is the destination, but in the Intel AT&T notation, the second operand is the
So
destination.
I equals X.
Hmm?
I equals X.
No, it's the other way around.
Load the data that is I. I
The
itself is not an address. I itself is the data.
I itself is the data. It is the bit pattern. If you specify I to be 0,
I is 4.
okay, so are we good so far?
I mean, here it's X equals I because we have the first one as the destination and the second
Correct.
one as the source.
That's
But on
correct.
the other slide is the opposite way around. Correct?
That is correct.
Okay, that's what I was asking.
All right, so but the point is, if it is an immediate operand, there's a $ in front of the expression. Okay, so that's the syntactical part of it. The meaning part is in column D because I'm trying to associate what we are seeing here with something that we already know. Okay. The next one is something that we have also encountered a lot of times. It starts with a % symbol, and then you specify a register. So it's called a register operand. Okay, not very surprising. Okay. So in this case, register can be any registers. Can be any register. So we have talked about the registers, EAX, EBX, ECX, EDX, ESP, EBP, and so on and so forth. There's a whole bunch of registers. It can also be AX, BX, CX, and DX, which are the 16-bit windows into those particular registers. Can also be AL, AH, BL, BH, CL, CH, DL, DH. Those are the 8-bit windows into the 32-bit registers. So we have talked about all of these in an earlier class session. It's also in the notes as well, okay, in the actual notes that are linked from inside Moodle. And I can make this, I can format this. Let's see, okay, I guess the format, go to text wrapping, and say wrap. There we go. Okay, so the name of this particular of this kind of operand is easy. It's just a register, and in our notation, it is the X and the Y. Okay, so in the case of LDI, the X is the one that is a register operand. So I'm going to boldface the X here just to emphasize, that's the one that we want to look at. Okay, boldface. There we go. Yep.
So if I understand this correctly, move the $0% EAX or AX would copy 0 into that register, right?
That is correct. Now, but that's a very good question. What if the suffix of move, which is B, W, or L, does not agree with the register that you specify? In other words, what if you say move B, $0 to EAX, %EAX, right? Because now you have a discrepancy. Because on one hand, you say, this is a move byte instruction, we're moving only 8 bit wide, but then you specify a destination register that is a 32-bit register. In that case, the assembler would actually complain and say, can't do this.
So
There's an inconsistency.
So you only need the right size to the right size register.
Correct. So
It's probably actual writing. Could you put a slash between which ones are 32-bit, which ones are 16-bit, and which ones are 18-bit, just to like help differentiate which ones?
all
are
the
which?
E's,
All
all the ones starting with the E are 32-bit. All the ones that ends with that do not start with an E but ends with an X, those are 16. All the ones that do not start with an E but end with L or H are 8-bit.
So there's only 4 16-bit registers, and there's.
Well, these are the ones that we're going to use. There are more registers than these, but these are the ones that we're going to use a lot in this class. Okay. All right. So we got register, and then we also got indirect register, which is represented by parentheses around registers. Okay, around a single register. So the parentheses in this case is not for arithmetic grouping in terms of calculation. It literally is needed in order to specify the reference. Okay, so when we put parentheses around a register, it is the same thing as the asterisk symbol in C and C++, which is the reference. Is that okay? So in this case, reg can be some of the registers, but it can only be any 32-bit registers. In other words, it has to be the one that starts with an E, cannot be any of the other ones. Okay. And the name of this operand is called indirect. Yep, go ahead.
Can you have a constant in there inside of the reference?
No. Well, it is not considered an indirect operand anymore, but you can have a constant in there, which is something that our processor does not allow. So in terms of equivalency to our toy processor, this is equivalent to the ones in parentheses in the LD or an ST instruction. Okay, so I'm going to use an example of LD. So the LD instruction is copying something that Y is pointing to into X. So this portion, okay, it doesn't. The formatting part of the Google spreadsheet is a little bit cumbersome, but it's not too bad. I can still get it done. Okay, so it's okay. It's just a little bit cumbersome. So the Y in parentheses part of an LD instruction or the ST instruction is what we call indirect in the Intel processor. What it does is it will say, okay, I'm going to use one of the 32 registers as an address. The content of that register is considered an address. I will go to that location and retrieve the content of that location to become the actual operand, the thing that is going to be used by the instruction. Is that okay? All right. So these three are the ones that we have in our toy processor. The next ones are the ones that we do not have in our processor. Okay, and this is why the Intel processor is called a CISP architecture, or complex instruction set computer, as opposed to the toy processor that we have, which is a very risky RISC. Okay, it is the most extreme RISC processor because it has basically just the simplest instructions that are necessary to get things done. Okay, so the next one is called a direct instruction, a direct operand, and all it is just some kind of expression, okay? It's some kind of expression that will give you a numerical value. Whatever that numerical value is specifies the address where you will grab the content. Okay? So this expression is really the same thing as this expression, but because you don't have the $ in front of it, this is no longer an immediate operand. This is now called a direct operand. And there's no equivalency in our toy processor because we simply do not have the mechanism to get this done with the current architecture that we have. Is that okay?
And so this, but it still has to be resolved at compile time, or at link time.
Yes, it still has to be resolvable at link time. But to us, it's quote unquote assemble time because I haven't really talked about the linking process. So we'll just use the assemble time for the time being because we have talked about the assembly process. Okay. All right. So now we can go ahead and specify some examples. Is this part okay? Are there any questions about these 4 quote unquote addressing modes? Yep.
Well, what's the difference between immediate and direct?
Okay, so that's what I'm going to
Oh,
clarify next.
all right.
Okay, so I'll use an example to clarify it. So for that, let me see. I'm going to use. I'm just thinking about whether to use. We can use a Google document for that. So we'll go back to the folder, make a new Google document. Yep, create it here, and rename it immediately and call that. Well, should I name it after today's date or should I give it a name like examples?
Date.
Hmm?
Date.
Direct example.
Okay, I think a date is probably better. Okay, because I don't need to specify the class name because this folder is only accessible to this class, and we don't have to deal with that. Okay, so we'll go ahead and start with a move L instruction, move long. Okay, now a lot of times you don't really have to specify the L. Because something in the operands, if it involves a register, it will imply what is the actual width of the operation. In the case that nothing in the operands will actually specify the width of the operation, the assembler would make a default assumption of 32-bit wide. So if you don't specify, it is either determined by the operands or it is just defaulting to 32-bit wide. Okay, but I always specify the width because I don't really want to leave anything to the assembler to assume. Okay, so we'll go ahead and specify this one first. Okay, okay. If I were to use a C notation to indicate the end result or the actual operation, the pound sign, by the way, is equivalent to // in the assembler. It is what separates what the assembler should see versus what the assembler should not see, comments. Okay, so everything to the right-hand side of the pound sign is considered comments for the assembler. So I can type anything I want after the pound sign. So this operation, okay, if I want to use the C notation, is simply to say register EAX gets a value of 0. And that's the end of it. Is that okay? And in
After the B, or is that L? Is that L, like move like long?
it's move long,
So move long 0.
$0.
Move long $0.
The dollar is very important.
And that's the expression. So move the long expression 0 to the register EAX.
Yes, but it is really just copying the value of 0, literally 32 bits of 0 to EAX. So EAX is now completely zeroed out. Exactly, very good. And in our toy processor, okay, it is equivalent to LDI. We don't have EAX, so I'm just going to use A as an example. So in our toy processor, is equivalent to LDI A, 0, which is just copying 0 into register A. Now there's no true equivalency because our register A is only 8-bit wide, and we don't have any 32-bit wide instructions. But as far as what is involved in the process, it's the same. Okay, it just grabs whatever 4 bytes is right after the opcode itself and say, okay, these 4 bytes is what I'm going to copy into the register. In this case, it's going to be 4 bytes of zeros because that's how we represent 0 using 32 bits.
And you couldn't say move W $/EAX because the size.
That is correct. Because if you use move W, then the assembler is going to complain and say it is not consistent.
Big for what you're trying to get into it.
Exactly. Yep. But you can use just move MOV without the L, then the assembler will say, oh, okay, I can see one operand implies this is a 32-bit operation, and then it will switch to 32-bit automatically. Okay. All right, so the next one is just move L0 into EAX. Syntactically, or if you just look at the text of this particular instruction, it looks almost exactly the same as the one before, except we don't have the $ anymore. Okay, but the meaning of this is entirely different. Okay, so we'll take a look at the actual meaning of this one. EAX is still our destination because it is the second operand. So as far as the second operand is concerned, there's no difference. But because the first operand now does not have a $, it is now doing this. Okay.
So move whatever information is at address 0
Yes.
to EAX.
Yes.
But what if the information is address 0 is 32 bits? Is it going to assume that's 32 bits?
Yes.
Oh,
so,
yeah. Okay.
so if you really want this to be
No, you have to add the.
No, we're good.
okay, so now it's much better, right? So now we know that, okay, we're casting 0 as a constant to be the address of a 32-bit unsigned integer. And then we dereference that. Yes? No? You guys don't like that? I think this is a lot more specific. Yep.
Speaking of which, for the purposes of these binaries, are we ever going to use numerical addresses? And if we do, does the assembler, or is it somehow just interpreted as the beginning of a particular memory chunk that's given to the given program?
Mm-hmm. Well, we seldom, if any, if at all, would use constants to specify an address. It is not usually, or I should say, literal constant. Okay, not a label. So typically, when you want to refer to the address of a memory location, you would use a label because you want to leave it up to the assembler to do all the counting for you, right? So the only time that you want to actually use a constant is when you are specifying your code in the firmware of a particular device or the boot up code of a computer, because at that time you know that you're starting execution at a certain location. There's no doubt about it. Okay, and then if you can make assumptions about the hardware configuration, you can also say, okay, I know for sure that RAM starts at this location. I'm just going to scan and see how much memory I have. So in those cases, you can start with a particular constant, but it's very, very seldom that you want to use a constant like this. Now, on top of this, because Linux is a protected mode operating system, does anyone want to tell me what that means? A protected mode operating system as opposed to a not unprotected mode, an operating system that is not running in protected mode. Okay. Sorry. Okay, Windows 98, well actually the last one is Windows ME, Windows Millennium. Everything up to that point, they are not running in protected mode, or at least not in the i386 protected mode. Which basically means, sorry?
Do they segment out the memory they use and make it inaccessible?
Well, okay, there are two aspects to it. But the most important aspect is in a protected mode operating system, each application gets its own space. And it cannot cross over the space to the space of another application. In other words, if you crash and trash your stack and your heap and stuff like that, your application dies. But it won't cause another application to die, but it won't cause the operating system itself to give you the blue screen of death.
That's why Windows crashes so often. That's why the older Windows.
That's why the old Windows crashes so often, because any application has visibility to not only the memory space of itself and of the other applications, but it also has visibility and access to the operating system itself. So when it does crash, it crashes hard. But in Windows NT or any operating system that uses NT as a kernel, that would include, from XP and up, all the consumer Windows are also NT based. So those are much more stable because the kernel itself is running in a protected space. The application can trash its own space, but it cannot trash the operating system's space. But the problem now comes from device drivers, because device drivers run at the same protection level as kernel code, But who writes the device drivers? It's not Microsoft, right?
Whoever does the hardware.
Whoever does the hardware. And what do you think is the quality control of those particular companies? Well, first of all, are those companies software companies or are they hardware companies? Realtek, Sound Blaster, just take your pick, okay? Those are hardware companies, right? So what are the chances that in a hardware company, they have a dedicated quality assurance person to make sure that their software is properly written and well tested?
So,
Yep.
but that would be an example of where you would actually use some of the exact addressing that would be device drivers.
No, not really. Well, okay, device drivers are special because they do not access memory space to talk to the I/O devices. They talk to the I/O space. We haven't really talked about that yet. But the bottom line is, if you do run this instruction, it will give you a segmentation fault because location 0 is usually not addressable to a end user application. Yep.
Isn't like C and C++ isn't null like the same thing as sending a pointer address 0?
Yes.
So is this technically trying to set it to null?
Well, but I'm not setting a pointer to null. I am actually dereferencing a null pointer.
Oh, I see. Okay.
Yep. Which will cause a segmentation fault. Without the dollar sign, without the asterisk at the very end here, it would be just saying that okay, EAX is 0, which is the same as the previous instruction. Okay, but then I'll be using a $0 instead of a 0 without a dollar. If you use a 0 without a dollar over here, it means that you are planning to go to that location to retrieve its content.
And then that's when it gives you an error.
And that will give you a segmentation fault. Yep. But it can be any expression, so it can be something that is actually valid that you allocate somewhere in your memory space. Is that okay?
This makes sense why my programs and data structures crashes all the time.
Okay, so the next one is something that we have seen also. Okay, so this one actually is something that we have actually performed in our class. Okay. Okay. So this one makes use of a new addressing mode that we haven't presented in this particular slide, but we did talk about it in the other one. So in this case, the source, or what is providing the data, is indirect, which means we are going to where EAX is pointing to and retrieve those 32 bits. And those 32 bits will now be copied to the destination, which is EBX. So the C notation to do this is saying EBX as a register is getting whatever EAX is pointing to. Okay, so that's the pseudo C notation. And for this one, we do have a equivalent command in our case. It is just the Ldi instruction. So we are doing a load into register B indirect from A. So A specifies the address and B specifies the destination. Is that okay? But there's no equivalence in terms of the previous instruction. We simply do not have the mechanism to do it with our FOIA processor. Okay. Well, the next one is just the reverse of this one. Okay. Okay, maybe we can do something like this. Okay, this is actually legitimate. Okay, you can do something like that. Okay. Okay, we're using two addressing modes that are two operand types that we have already seen on this slide. Okay, so in this case, the actual C command or the equivalent C command is to do something like this. It's a dereference uint32_t, but this time I'm using 5 as the actual address. So this is the equivalent representation in C. We are using 5, which is the second operand, but it's a direct operand because it doesn't have a dollar sign in front of it, right? So we are now using 5 as an address. Then we go to and then we store the zeros into location 5 of the memory space. Just like location 0, location 5 is usually not accessible to an application, and as a result, this will also generate a segmentation fault. Are we still doing okay so far with all this stuff? Good? Okay. So let's switch back to the spreadsheet here. So I'm going to introduce some additional addressing modes, but instead of using the kind of more gradual approach, I'm not going to give you the worst addressing mode, and then we'll kind of go back and say, okay, but we can cut off portions of this thing so that it becomes a simpler type of addressing mode. Okay. So the most complex addressing mode looks like this. We have a base register and an index register, and optionally a scale. Okay. And certain portions, some of these are all optional, so I have to say that this is optional as well. Okay. It's really hard to specify, which part is optional, but this is the best I can do because, at this point. Okay. So this is a very special addressing mode. So in this case, breg and ireg must be 32-bit registers. Okay, they can be the same too. And then scale can be 1, 2, 4, and I think 8 is an option as well. So it can be 1, 2, 4, or 8. Okay. We don't have an actual equivalent command here because this is basically the height of cisp instructions. Okay. So what I can do is to tell you how we compute the actual address. Okay, what does it really do? So with this, I'm going to say this is called the based indexed scaled addressing mode. That's the name of it. Okay, it's a very awful name, but Intel decides, hey, this is how we want to call that. Okay. Okay, so we'll go ahead and use this column to indicate the C notation for just that particular operand. For immediate, I is really just I. Okay, we're not doing anything with I. I is just a constant. With a register, it is just the register itself, which is just the register itself, X. With indirect, we are dereferencing. Okay, whatever operand you specify, we're dereferencing it. With direct, it is kind of the same thing, but we are dereferencing a constant value. Okay, I has to be determined by the time we assemble the file, the program. So in this case, we have two registers and a particular expression. So now we're saying, okay, where is that operand? What operand are we specifying? Okay, so this is the big, huge mess that we have to deal with. Okay. The huge mess that we have to deal with, I'm going to specify the expression first. Okay, the expression is also, once again, something that has to be determined at assemble time. Okay, so it's 1, 5, -2, or whatever you want to specify. And then we have to add something to it. What we're adding to it is kind of complicated, so we'll use parentheses. We will put stuff inside the parentheses. The base register is just a base register, but then the index register, I register, has to be multiplied to the scale. Okay, so this will give you a particular value, right? This is just the expression, which is a constant, plus the value of the base register at the time this opcode executes, plus scale, which can only be 1, 2, 4, or 8, determined at assemble time, times the value of the I register or the index register. So after we do all this computation, what do we do with this particular value? We dereference it. So now we have the last operation, which is to dereference it. Yes.
Why don't you just specify the location instead? Why do all the calculation of that? Why not just say, dereference location, whatever the hell it will be, because that's going to be different every time.
Because this is really helpful when you have to deal with accessing an element in an array and specify a particular offset to that thing.
So expression would be a number you know that gets you the right answer.
Okay, let's just look at this one. Okay, so I will go back to the other document just to give you an idea of why this can be useful. Okay, so this time I'm going to switch to here and use just a little bit of C code. Okay, just a little bit. Struct X is defined as follows. Okay, I'm not going to make this too complicated. We'll just go ahead and say this is uin16 underscore t x and uin16 underscore ty. Okay, semicolon, semicolon. There we go. But what I want to do with this is to say I want to make a variable out of x, but this is not just any variable. I want to make an array out of it. Okay, the length of the array is not even important. Make it 6 long. Okay. All right. So A is an array of 6 struct x's. Each struct x has 2 members. X and y are the members. For those of you who have never seen struct, because the only thing you have seen is class, struct is like a class where everything is public. That's it. Okay. All right. So in this case, if I tell you where A is, how do I get to? Okay. So let's see what we're dealing with here. Okay. So what is the address of A bracket, I don't know, 2 dot y? How do we get there?
First the matrix.
Now we're assuming the compiler is dumb and we just kind of contiguously allocate stuff. Okay. How many bytes do I need for a single struct x? That's the first question. How many bytes do I need?
Oh, 32.
How many bytes do I need?
8 bits is a byte.
8 bits in a byte.
4 bytes.
4 bytes. Very good. 4 bytes in a single struct x. Okay. And as a result, the array has how many bytes? 24. Very good. Okay. So I want to access this thing here. Okay. A bracket 2 dot y. So now I can say, well, let's go ahead and put these things into different registers. Okay. So I can put the 2. Okay. So I can say the base register. Okay, I'm going to use EBX as a base register. So I can say EBX has a value of 2. Okay, to indicate the base, not the base. This is the index register. And then the base register, I'm going to use EAX to represent it. It's going to be the address of A, the entire array A itself. Come on, A. There we go. And by the way, ampersand A and A are really exactly the same thing in C and C++, because if you just refer to the name of an array, you are automatically referring to the reference or the address of the array, because there's no way to pass an array by value at all in C and C++. So ampersand A is really exaggerating that we're taking the address off. Okay. And now we're going to say, okay, what about y? How do we account for y? Y is actually a constant because it is the number of bytes from the beginning of a struct x. What do you think? If you think the compiler is really dumb and it just allocates bytes sequentially, what do you think is the displacement or the offset from the beginning of a struct x to the y member? 2 bytes. Okay, 2 bytes. Okay, very good. So we'll say 2 is the offset of member y from the beginning of a struct x. Would that work? Okay. So now, in order to put something into a bracket 2 dot y, I can use a single instruction to do it now. Okay. I can say move w because it is only 16-bit wide. Let's just say that I want to put a 0 into that thing. Okay, so we put a 0 into it. And let me scroll up because people in the back probably cannot see it. Okay, and then the destination. Okay, so because I want to do this. Okay, this is what I want to do. Okay, this is what. Whoops. Ah. Okay, this is what I want to do. This is the instruction to do it. Assuming. Okay, let me just kind of write down here. This is what I want to do. This is what I am assuming. This is the instruction to do it. Okay, there we go. Pretty clear. Clear to me anyway. Okay, so what do we do here? Come on, we have to kind of put all of these things together. Okay, and there's one more thing too. Okay, size of struct X is 4. Okay, very good, because it is important. Okay, so now how do we use that really, really long and super complex addressing mode to specify, hey, we want to access a2.y. We start with the offset, okay? We start with the offset, which is a constant, which is the 2, okay? That's our constant. And then in the parentheses, we have 3 things. The first one is the base register. The base register is essentially, let's start here, okay? And then we'll just nudge the address a little bit after that. What do you think is the base address? EAX is the base register. Very good. The next one is the quote-unquote index register, which in this case is pretty darn clear what it is. EBX is our the index register. And what is the scale, which is basically the multiplication thing, which is the 4. The 4 has to be a constant. Now do we see why Intel says, hey, let's go ahead and make this really, really complex addressing mode.
Take care of this one circumstance where you can do this one type of thing.
Yes.
One time, instead of having to do it in 4 steps.
Exactly. I cannot remember the order. Go ahead.
Do you put 4 or $4?
It is just 4. So inside the parentheses, you do not need a dollar sign. It's either 1, 2, 4, or 8, because that position cannot specify an address. It is always a multiplication coefficient to the index register. Yes.
So
he's first. Okay, go ahead.
So how long would it take to do this without the base register and index register?
Okay, so we can do that. Okay, so we'll try to do exactly the same thing, but using the toy processor that we have, and then see how much work is involved in here.
It's probably a lot.
It's a lot more. Yes.
Is to be defined using this addressing mode as pointing from EAX as the starting member of the structure, EBX being the actual offset itself, that's the number it's looking at, and then 4 just being the size to
Of each item in the array.
4 bytes every
Yeah. So EAX is the base, which is where the entire array starts. EBX is the index, but you have to multiply the index by the size of each element to get to the starting point of a particular element.
Well, that makes sense, but I'm just asking, is it, when it is assembled, is it basically replacing the 2 with the information that's stored inside the parentheses?
You mean the 2 here?
Yeah, that 2. Is 2 just like a name that you're giving the...
No, 2 is added to it. So if you go back to the syntax of this particular addressing mode, this is the actual effective address. This is the actual place where you're specifying. So the expression, which is what is outside of the parentheses, is really just a constant that you're adding to what is inside the inner parentheses. It's just an offset, constant offset.
And we're using it to offset to what position?
We are using it to offset to the correct member inside the structure.
Each member we define as being 2 bytes
Yes.
wide.
Yep.
Okay. Then where do we get the scale as...
The scale is the sizing, is the size of structures.
Okay.
Yep.
Go back to the other document real quick.
Uh-huh.
We got those 2 lines. Yeah, we got those 2 lines in the percent EBX is equal to 2. Why is there 2 equal sign?
This is just equal to 2. I'm assuming it's the index register. Yeah, so this 2 is coming from this
You're
2
not
here.
actually doing anything there. You're just kind of showing us that it's
Yes,
okay.
and that's why I use double equal, which means that's just an assertion that EBX has a value of 2, EAX has a value that is the address of the array. Yes?
When you said size of struct X equals 4, why is it not 6?
Why is it 6?
Huh? Why is it not?
Why should it be 6?
I thought because you said struct X A, or actually 5, because the struct X is an array, it's 6.
but I said size of struct X, not size of A.
Yeah, we're asking how big is a struct, how many bytes is
In a struct, not the entire array. Not how many elements are in the array, but how many bytes do I have in a single struct.
it? And the struct has two 16-bit integers, which is 32 bits. You divide that by 4. Yes. Or 8 bits is 1 byte. So it's 4 bytes.
Yep. Okay. So, do you guys want to see, what it will take for our little poor toy processor to do exactly the same thing? All right, let's do it. Okay, so in terms of the toy processor, okay, so using our toy processor, and we'll make some assumptions first, okay? Assuming, okay, so in this case, I'm assuming that we have the B, register B, having 2, which is the index. We assume that register A is the address of A. So this is a starting condition. Okay, don't ask me how I got these values into register A and register B. It's just given to me as such. Okay. The other two are going to be exactly the same because I cannot change these two assumptions because these two are based on the C code that we are dealing with. So that cannot be changed. So now, how do we do this? Okay, first of all, I have to trash at least one other register. There's no way for me to avoid trashing one other register because there's no way for me to do computations based on the registers and then do the dereferencing without destroying at least one other register. So we have to sacrifice. Huh? Overwrite. Overwrite one of the registers. So I'm going to pick register D as our kind of scratch pad register. Okay, so we'll see what we need to do in this case. So the first thing we need to do is to say D equals to the index register, which is B, okay? But that is not taking into consideration the scale, right? Because we have to deal with a scale of 4, which which means we have to do something about this. We don't have a multiply instruction. How do we multiply the value of D by 4 without a multiplication instruction?
Add it 4 times.
Not 4 times. Twice. We only need to do it twice. Because we can do this.
Oh, yeah, okay, 2 to 4. Powers.
We can do this, right? So now D is 4B, okay, at this point. So then what do we do? Okay, remember D is our sacrificial register that we can override to get this job done, right?
We should take the value that it is and save it in a memory location somewhere so we can get back to it later since you're going to have to write over it.
No, not yet. We don't have to do something like that. We have one more register that we can trash. But before we trash that other register, we have something else that we can do. We have to do first. Okay, so now we have the product of the index register times the I scale from the scale, right? What do we do after that? Okay, let's go back to the other slide, and I'll highlight what we have done so far. Okay, so what we have done so far is we have this product now. Okay, that is now in register D. What do we do next?
We have to add the value of register.
Of the base register, which is register A. Okay, very good. So let's do that. So we go back here and say A equals, whoops, D equals D plus A. Okay.
So this is us moving through to position.
So now we have this part. We have everything inside the inner parentheses done. We still have the expression not done yet. Okay, so I now have to use register C because I don't want to destroy register A or B because nobody told me that they can be overwritten, so I better not do that. So I'm going to use register C. And expression is something that has to be resolvable by assemble time, which means I can use the Ldi instruction. So if I go back here, I can use the Ldi instruction to load something into register C. So C equals star PC plus plus. PC plus plus, and in the comment I say PC, whatever is at PC at this point has to be, in this case it's a 2, yeah, it's a 2, there we go. And then after that we just add the 2, so we have D equals D plus C to add that one constant, that single displacement to what we have so far, and then finally we can do the dereference, okay? But then we also have to put a 0 into one of the registers first. So we have to put a C equals star PC plus plus again. But this time PC is pointing to a constant of 0. Now we can finish the whole operation by saying, go to where D points to, change it to whatever register D has. These are the instructions that we need to do using our toy processor. The Intel processor can do it with one single instruction.
Doing it this way.
I would say
the
so.
The long instruction than the short instruction, just because I can see step by step what I'm doing. Like even though it's like more work.
It's way cleaner.
It's cleaner, yeah, but this
Honestly,
makes
I think
more sense.
no,
It makes more sense what's happening. Like,
I'm just converting all of this into the instruction set or the mnemonic.
Makes more sense to me.
I understand them both. I'm just saying for like coming at this like say that like I'm just walking class right now. I would know exactly what he's doing right here and what the results are going to be. Versus the other one,
I don't know.
even if you explain it to me right now, it would still be kind of fuzzy.
There we go. All right. So now we have a fairly sharp comparison between CISC and RISC. So the reduced instruction set computing, okay, is reducing the complexity of the processor itself, so we end up using fewer transistors. But we are going to sacrifice in terms of execution code, or the opcode that we have to store in RAM, because now it takes quite a few more instructions to get the same thing done. But we still do okay so far. Can somebody remind me, because this is just counterintuitive. So why do we like RISC? Okay, why don't we just say, okay, Intel wins, it had the right idea to begin with, and ARM and all the other RISC companies got it wrong, because now we need so many more instructions to get the same thing done. What is the trade-off that makes RISC actually the processor architecture of choice these days rather than CISC?
Because of heat.
Because of heat, okay? But it still doesn't seem to make a lot of sense, because if you think about it, executing this one single instruction would use an X amount of energy, right? Executing this entire sequence of 8 instructions would also have its own heat amount of energy that it takes to execute. So why do they this one single instruction is going to take up more energy compared to these 8 instructions altogether?
Complexity.
Yeah.
The complexity in terms of transistors, exactly. Okay, because in order to do the complex instruction like this one here, it would take a lot more transistors to get it done, as opposed to the processor that has to do this. Okay, which one is going to be faster? Okay, at the same clock rate. Okay, at the same clock rate, assuming reasonable implementation of the instruction, which one is going to be faster in terms of just how much time it takes to execute this one single instruction as opposed to how much time it takes to execute these 8 instructions? The CISC one is going to be faster, okay? But it's going to use up more than 8 times the energy of the longer version. And that's the trade-off, okay? Because the data processing centers are not limited in terms of space. They're not limited in terms of how much energy they can pump into the building. They're limited by how much heat they can extract out of a building. So that settles it, right? Because now instead of using a single Intel processor that can do this in one single instruction, we just say, fine, we'll use 12 processors, much slower, but each one being simpler and use up less energy to do this.
Is that CISC or RISC? I forget.
The highlighted portion is RISC. It is because the instruction set itself is reduced. So we need more instructions to get the same thing done.
So would the RISC processor be preferred for Bitcoin mining?
Every time it's really preferred for just about any type of processing, except when you want to run your good old DOS game without emulation. That's the only time you say, oh, I need an Intel processor. But for everything else, RISC is better. There was a question back there. No? Okay. So are we doing okay so far with this particular discussion? It is still, a lot of this material is actually in the notes that I have linked in Moodle. It's just that the presentation this semester is tying all of that stuff to the toy processor, which is new, and it is not fully documented in my notes. Yep.
Are we actually going to use this particular move command?
You mean this one?
Yeah.
Oh, yeah. Now, there are special versions of this, okay? There are special versions of this where you can take out certain portions. For instance, you can take out this entire portion, okay? So you keep the EAX and the 2 on the outside. Then it is called just the based addressing mode, which is exceptionally useful when we need to access local variables because they're on the stack, they're all pointed to, there's a fixed point in stack that we refer to as the frame pointer, and they're going to be a fixed offset from the frame pointer. But we are not getting there yet, okay? But this turns out to be a very useful addressing mode, and that's why some of the RISC processors actually implement this particular specialized addressing mode because it makes sense, okay? Because sometimes, you know, okay, let's just, we are running out of time, okay? So I'll just make this point here. This one here, okay. This is, if you ask anyone for a minimalist, okay, RISC processor, this is close, okay? If not exactly it, this is really, really close. So from the perspective of, you know, this is a pure RISC machine, we're good. But in terms of being practical, it's not practical. Because your compiler has to generate code to run on the processor. So if your compiler has to keep generating those a sequence of 8 instructions over and over again, it's not being efficient. So sometimes it pays off to put a little bit more transistors into the processor, and you get more return out of those, you know, extra transistors in the end because they are utilized a lot. Okay, it's just that when you put extra transistors into the processor, but you seldom use those transistors, then it's a waste. Okay, so we are running out of time, so I cannot, you know, go any further at this point. We'll go to the lab. If you guys have any questions, you know, if you study, if you have any questions about the material, I can answer those questions in the lab. And of course, we have to remember to save the recorder.